demo I didn't get to yesterday. So what this is it's a bag, a long bag. It's sealed at one end and open at the other. So if the goal is to inflate the bag, how could we inflate the bag?
With air.
Yes. How would we put the air in the bag?
Through the hole.
Air nozzle.
Could use an air nozzle. Okay. So we could take our air hose. We could inflate it. Yep. We could inflate it with the air hose. Okay. How else could we put air in the bag?
With your mouth.
We could put. We could go. What was that for? Then we got some air in the bag, but I didn't fill the air. But we do have some air in the bag. Okay, we can do it that way. I am a little lightheaded. Thank you for whoever asked. I am for your concern. I appreciate that. How else can we put air in the bag?
Right? Wind.
What?
Wind. Yeah, that.
Like outside, probably.
Oh, okay. Yeah, so if it was windy out, we could hold it in the wind. That would be good. Okay, but there's not a whole lot of wind in here, so
You gotta make some.
Try to catch it like a jellyfish.
we could try to like.
Whoa! Be careful.
I didn't run very fast, apparently. Okay, but we could, right? We could run and we could catch it. We could. I saw kind of like a garbage bag, right? Got some. Got a little bit more. Okay. Anything else? None of these, for the record, are Bernoulli's yet.
You could fill it with water and then evaporate the water.
Put on the back of the car and start
I
driving.
probably have to go ahead and battery.
You could like sit in the back of the truck bed and like hold it,
Very long
and they start driving.
Kind of the wind idea then, yeah. Kind of like that wind idea. I was confused by the fill it with water
Well, when you
and evaporate it. But this,
Parachute.
Technically, kind of.
no. But yeah, yes. I think teachers are not supposed to say no to students and their ideas. So,
Yeah, you're not supposed to. You're supposed to support
No
our.
idea is about
so close. I think is what we're supposed to say.
Yeah.
You're on the right track.
You're not there yet.
You're not there yet. The power of yet, as my elementary children call me. Bernoulli's. High to low pressure, right? But what about high to low pressure? How can we create high to low pressure differences?
Fast versus slow.
Fast versus slow, okay?
Right.
So how could I get, so what could I do then, fast versus slow air here? Because when I went like this, I created a difference in pressure, right? High pressure, low pressure. But how much air went into this with every breath? However much is in my lungs, right?
Yeah.
So how can I cheat and get a little extra? Bernoulli's, okay, good.
Get bigger lungs.
Yes, I could get bigger lungs. That's not what Bernoulli's
Not quite
did.
there.
So if we take it and we go
What the heck?
down the middle,
What?
okay?
Do it again. Do it again.
So if we take it, okay, okay, if we blow down the middle, it kind of sort of cheap by holding it up, but it kind of just keeps it. And we go, okay, so that was one breath. I think I only got like this much with like 4 breaths before. Okay, so what happens? So when I go, when I blow fast moving air, okay, there's that amazing wind tube. And when I blow right down the middle, compared to the air here, is this out here and here, is this fast or slow moving air? Is this fast moving air compared to out here being relatively slow moving air? Bernoulli's principle says that the faster a fluid moves, the lower the pressure. Okay, so that means this is relatively low pressure compared to out here being high pressure, and out here being high pressure. And which way does pressure flow, from high to low or low to high? Air compressor, poke a hole in it.
High to low.
It always goes from high to low. So as I blow this fast moving air at low pressure, it actually will pull additional air in from the sides. Which I'm kind of surprised you guys didn't pick that up after I did my amazing hairdryer demonstration the other day. Remember with that hole punch that just stayed perfectly and never fluttered away and never got sucked through? Remember that amazing demonstration?
I think it's a little bit confusing because its demonstration was not.
Because I didn't do a very good job of doing it. Oh, maybe that's why you did. But that was the intent of, that's the same idea, that just didn't show very well. But if we get fast moving air through the middle, we create low pressure and it's going to pull in some additional air, just like the holes on this thing. Same idea with this thing. Now, we could turn on a hairdryer, right? And the same idea should work. Like, that's a sign to just stop using the hairdryer, I think, today. So never mind. We'll move on. But the idea is if I could somehow get that bag around this part, but not those holes, as it blows the air, it should pull extra air, and it would ideally fill up faster than if I were to put it just over this. That's should. Whether it actually does, I don't know. Okay. So that's Bernoulli. That's one of probably my the ones that I tend to screw up the least amount. Okay, so. Alright, so we'll do one more right now, and then we'll do a problem, then we'll do one more, and then we'll do a problem. So this is like the cardboard that you find in a carpet roll. So like when you go to like a carpet store would buy a roll of carpet, this would be like the tube on the inside that someone cut and they glued some sandpaper to. And then we can take these styrofoam balls and we can take them and we can throw it. Okay, we can throw it. And then what happens is this just kind of slides along the cardboard, nice smooth surface, until it hits the sandpaper. So it's going to slide, and then once it hits, it kind of grabs it and it starts to tumble. So the idea is by using this, we can create extra spin on the ball, and hopefully someone can help me out who's baseball or softball. But the idea is that we can take this, warning, throwing projectiles into the crowd, and it might hit someone, but it's a styrofoam ball, so hopefully no one gets concussed. But the idea is we can take this and I can throw it, and depending on how I throw it, it can either curve or can rise or can drop or whatever. So if I take this and I can kind of curve it, I'm going to try to throw it at the camera, which means you guys are kind of right there.
What if you hit the camera?
It's okay. So we're going to throw it towards the camera, and then we should, which means heads up, just for the record. And we're going to, whoa, that didn't go towards the camera at all. All right, try that again. Okay, ready? Here we go. Getting a little closer. Okay. Now, what do you notice about this ball?
It's curving. It was curving.
It was curving. It should curve. Okay. Should curve.
Just throw all three at once now.
Should curve. There's one more out there somewhere.
Gone.
Thank you. Okay. So it should curve. So I'll try to go across room just because then we can kind of go. Okay. Right? You saw it curve. Hopefully. Go the other way, just so everyone gets the equal opportunity to be scared for their
lives.
Oh, head no!
Suing the teacher now.
Okay. Yeah, you're good.
Yes.
Okay. And then so we can make them curve, but we can also make them like rise, or we can make them sink. So if we go like this, we should be able to.
Whoa!
I couldn't see what I was trying to do.
It didn't. You were scared and couldn't keep your eyes. Okay, so we should be able to try not to hit the same person. Okay, you saw it kind of rise, hopefully. Saw it rise. And we can also make it sink, but that's gonna come in. Try to go over here. Be good. See? You see it sink?
Yeah.
Okay. Because it spins, by creating some spin, I'm pretty sure, at least I'm not 100% sure. There's 3, there's 1, there's 2, thank you. And the third's back there, perfect. So the idea, I believe, is that when you get this ball to spin, you create these like little, almost like a mini current, I believe. So when the ball is spinning, you create areas of different pressures, which then cause the ball to move. Curveballs, stuff like that, and baseball, softball. It's all about spin on the ball, right? Someone who knows what they're talking about here. Right, so you gotta put some spin on it. Which I was really surprised to find out that a curveball doesn't actually curve. I found that out just a few years ago. It's always assumed it drops, right? A curveball actually drops, which I always thought was weird. Why wouldn't you call it like a dropper or something? But apparently I was in charge of baseball when that happened.
Curveball sounds better.
Yeah. Because what do we call it when it does curve? Then that's a slider? What's that?
Slider, or if it's going away from your throw, if it's going towards the throwing arm, that's a 2-seam. If it's going away, it's a slider.
And that's, the 2-seam refers to like how many seams you're holding the laces
it
on?
doesn't, the slider's more what's actually doing the 2-seams. Just,
Gotcha.
I feel like a slider would have been a better name for a curveball because it's like going down.
Because there's different types of curveballs. That's the thing. So a 12-6, yes, is the one that drops, but plenty of people
I bet
throw
just
it at
throw
an
the
angle.
ball straight.
So like I throw mine at an angle, so it does technically curve.
And
I
drop.
literally.
And drop. It does both.
Rex,
Yeah.
do you play?
It's a
Really?
slurver. Alright. And it has to do with the laces though, I'm pretty sure, right? Laces have something to do with this? If you didn't have laces, it wouldn't curve like it does?
Not necessarily. The laces are there to help put pressure on the ball to influence the curves, but it would still curve.
So it's more that you have something to push off of then?
Yeah.
Okay.
To increase our.
Gotcha. So like if you were to try to do it with like a tennis ball, wouldn't you do it as well?
I can throw a curveball with a tennis ball, but it's not as good as it would be.
What about softball?
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 Anything? No. H?
You're going. I'm not.
We good? You want anything? Okay. All right. So, so that by causing spin, it creates like these little differences, and that's how it kind of moves, I believe, is my understanding of the curveball and fastball and stuff. So, let's do a calculation or two from the worksheet yesterday called In Class. So, In Class Bernoulli's is the calculation that we're going to work on. So on the worksheet called In Class Bernoulli's, I misnumbered, but we're going to do number 4 found on the back. We're going to do number 4, which is really like the 5th, but it's the one that says 4, and it's found on the back of In Class Bernoulli's. Now there are some notes that we filled in on the front. We'll come back to that that very first calculation, the second number 2, for that last problem. But so we have a pipe that has a radius of 0.11 meters and has water flowing through it at 0.2 meters per second. The pipe then goes up 0.8 meters and the radius decreases. Okay, so we have a pipe that goes up and we have a pipe that gets smaller. So that's my attempt at drawing that pipe. Now you could draw an angle, it's just, I don't know, more like a hose. I'm kind of drawing more of a hose than a pipe, but it doesn't really matter. So the pipe then goes up. If the pressure in the pipe at the second location is 1.013 times 10 to the 5th pascals, what is the pressure in the pipe at the first location? Okay, so this is a 2 location. We have a location 1, we have a location 2. At location 1, we have an R1, and at location 2, we have an R2. So at location 1, we have 0.11 meters. And up here, we have an R2 of 0.056 meters. So it gets small. At location 1, the water is flowing through the pipe with a V1 of 0.2 meters per second. I know it's velocity because it said meters per second. Now up here, there's going to be some velocity too. It doesn't tell me what it is yet though. Okay, so there's going to be a V2. It tells me that my P2 is equal to 1.013 times 10 to the 5th pascals. Our ultimate question that was being asked is, what is my P1? And there's one more thing we should label on this picture, and it has to do with our H1, and it has to do with our H2. So it's saying from here to here, from the center of the pipe to the center of the pipe is 0.8 meters. So if we use that information, what would be a good thing to call H1? 0, okay, I like that. And if H1 is 0, then what's H2? 0.8. Now, could we call H2 0? Sure, then what's H1? It'd be what?
From 0.
Nope. If H2 is 0, then H1 would be
Negative.
negative. 0.8. Yep, it'd be negative. Okay? So how do we find pressure? Pressure, we use that really long equation called Bernoulli's. But Bernoulli's principle states the faster a fluid moves, the lower the pressure. If the blank changes, then the blank changes, so you must do a flow rate problem first. A1, B1 equals A2, B2. What was the first blank? If the blank changes, if the area changes, then the velocity changes. Does our area change? Yes, because our radius changed, right? So our area changes, so therefore our V1s and V2s change. Now what if my A1 and A2 were the same? Then my V1 and V2 would be the same as well. Okay? So we're going to have to do an A1 times V1 is equal to A2 times V2 problem. That's a flow rate problem. So we're comparing the flow rate here to the flow rate here, and those flow rates are constant. They're the same at both locations, but the velocity of that water is going to change because my area is going to change. Now, if you weren't sure if the area remained the same, what happens to your velocity? You could plug in the same areas at location 1 and location 2. Like if your radiuses didn't change, you could plug in A1 and you could plug in your A2 that have the exact same value, and then you get the exact same velocity. So if you want to, you could. Now the way I've been doing these area calculations, I've been solving for A1 separately, and I've been solving for A2 separately. Just for the record, some people like to, I'm going to erase this in a second, but some people just like to put the area formula right there, right? Because this is area at location 1, and this is area at location 2. So you could. I've been doing them separate just to try to keep things a little bit more sequential. So if A1 is equal to pi times R1 squared, we have to take my R1, which is 0.11, and we'll get our A1, and that's going to be in meters squared. Okay? And I'll do that in a second. Then I'll have to find A2, and that's pi times R2 squared, so we take A2, and that's pi times 0.056 squared, and that's going to give us A2 in something meters per second, meters squared. So if we go pi times 0.11 squared, we get a value of 0.038. Store that in my calculator. And if I take pi and I multiply by 0.56, 0.056 squared, we get an A2. That's equal to 0.0099 meters squared, with a whole bunch of extra digits. Okay, now we can do a flow rate. So if my A1 is 0.038, da 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 da, times my velocity at location 1, which is 0.2, that's equal to 0.00099 times V2. So if we take our area at location 1 times 0.2, and then we divide by our area at location 2, we get a V2 that's equal to 0.77 meters per second, with some extra digits that I'll store in my calculator for a later time. So that is my velocity at location. That's my velocity at location. I do a flow rate first. Then we start looking at Bernoulli's. Bernoulli's is really long. P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. There, now you can't accuse me of being monotone. I changed intonation. Fluctuate in my voice. Okay, so that's Bernoulli's. It's long. Hopefully we can cancel some stuff out. I often start with, did we define anything to be 0? Now, when I say anything, there's really 3 numbers we're looking at here. We're looking at P's, we're looking at V's, and we're looking at H's. Okay, so we're looking at kind of those 3 things. Of those 3 things, did we define any of those to have a value of 0? Yes, which one?
H1.
H1. So H1 is 0, so what's rho times G times 0? 0, right? So I often start with that. Is there anything we define as 0? Because 0 times anything is going to be 0. Anything else we defined as 0? No, I don't think so. Then, on the front of this, that last thing before the second number 2, it says, if a variable is the same at both locations, you can and should cancel out the entire chunk with that term in it. So, is P1 and P2, those are the things that we're looking at, are they the same at location 1 and location 2? I don't know, we know that value, we don't know that value, so probably not. We're solving for this one, right? So we gotta keep those. Is my V1 and V2 the same? No. Okay? Now when would V1 and V2 be the same? When your A1 and A2 were the same. Okay? So these are not the same. Is my H1 and H2 the same? No. So we can't cancel any chunks out at this point, but that's kind of what we look for. Now we go through, we start plugging numbers in. P1 is our variable we're solving for. This is talking about water flowing through a pipe, so the density of water is 1,000, so 1/2 times 1,000, times our initial velocity of 0.2. Don't forget to square it as v squared, plus 0, which we don't need to have, plus P1, which is 1.013 times 10 to the 5th, in scientific notation, move that decimal point 5 times to the right, 101,300, plus 1/2 times the density of water, which is 1,000, times our new velocity that we just calculated, 0.77 squared, plus the density of water times 9.8 times 0.8, because that's my H2. Shoot, I just wrote over one of my numbers. Pi times. Okay. So 500 times. All right, so P1 plus 20 is equal to 113 times 10 to the 5th plus 297.75 plus 1,008 of 78,000 or 7,800. So then we take those numbers, combine like terms. We gotta subtract 20. Subtract 20. And we get a P1 that's equal to 109,417.7 pascals. So 101,000. 109,000. 109,417.7 pascals. We had to do a flow rate problem first. Once we did a flow rate problem, then we can plug it into Bernoulli's. Once we plug it into Bernoulli's, we can solve for P. Well, we could solve for H1 or we could solve for H2. We could solve for V1 or we could solve for V2. We could solve for P1 or we could solve for P2. That's what Bernoulli's does for us. We could solve for either of those. Okay, so here, piece of paper, some of you get some biology concept maps. All right, so this is just a piece of paper, nor what's actually on the piece of paper. It's just for a demonstration that you're going to do. So, Bernoulli's says the faster a fluid moves, the lower the pressure. Okay, so if I take a piece of paper and I hold it like this, and if I were to blow across the top of my piece of paper, okay, so if I take my piece of paper and I hold it like that, and if I blow air across, is that fast moving air or slow moving air compared to down here? That's fast moving air, okay? Compared to down here would be slow moving air. So what I want you to do, thinking about that, is make a prediction. If I blow air across the top of my piece of paper, is my piece of paper going to stay exactly like it is? Is it going to get pushed down, or is it going to be lifted up? Make a prediction first, then you can try it. So just hold like this and blow over the top. Gotta have it. Gotta make sure it can float. Oops.
It's pretty floaty to me.
Okay. So I kind of hold it like this because if you hold it like this, it doesn't really work quite. Gee, I guess always kind of like. What does it do? It goes up, right? So it should rise because the faster a fluid moves, the higher or lower the pressure? Lower the pressure. So this is lower pressure, where this is higher pressure. Okay, and which way do fluids flow? From high to low or low to high? They're going to flow from high to low, which means that piece of paper is going to be lifted upwards. This is a 2-for-1. You can use 2 pieces of paper for 2 demonstrations. Now we can take that piece of paper and we can rip it in half, hamburger style. Doesn't have to be perfect. Okay? And then if we hold our pieces of paper like this, okay, but now we push the 2 pieces of paper together, and then we're going to blow right down the center. Okay, so we'll take these 2 pieces, and we're going to blow right down the center. Before you do though, you should make a prediction. Are the piece of paper going to get blown together, get pushed apart, or do nothing? Make a prediction first, then try it. Now basically all it is it's kind of going like hold it like this.
Whoa. You're just giving us permission to avoid this.
Okay? I can recycle those for you if you'd like.
If you want, yeah.
If you would like, I can recycle. You're welcome. Okay? So, amazing Bernoulli's demonstration, Mr. Davies. Thank you. Can someone grab that? Thank you.
I'm not upset.
What about paper?
Thank you, thank you. Okay? So remember, at some point, you're going to be expected to explain one of those amazing Bernoulli's demonstrations that I've done over the last couple of days. All right. While I'm erasing this, we might as well talk about that. So my plan is today, I'll get you a worksheet to get started on today. You won't have a lot of time because we have one more calculation to do. Then we will have tomorrow to work on the Bernoulli's worksheet, which will be the final worksheet of this unit. On Thursday, we'll have a little bit more time as well as some progress quiz stuff. And then Friday will be a Socrative review. And then we'll test on Monday. Okay, it's a Monday test. Yeah, I know, it's not great, but we're doing it Monday. Okay, so we're going to test on fluids on Monday. Just so you're aware of that. Number 6? 5. This is number 5. So on that in-class problem called in-class Bernoulli's, problem number 5 kind of goes back to our first calculation we did, and I'll address that in a second. So we start with a large tank, and that has a radius of 1 meter. Okay, so we have a radius of, oop, I got a little ahead of myself. We have a tank that is 4 meters tall and has a radius of 1 meter. Huh. I don't actually ever mention that this tank is filled with water until the very end. I should probably change that. There's a tank filled with water. A large 4 meter tall tank is filled with water and has a radius of 1 meter. And it develops a small hole at the bottom in which water is going to come out. That was supposed to be an arrow. That was not a good arrow. And the water is going to come out. Okay, and it has a small hole. And that hole has a radius of 0.04 meters. If both of the holes are open to the atmosphere, what is the velocity of the water coming out of the holes on the bottom? Okay, you can assume the water level is constant and the velocity is 0 at the top. That takes us back kind of to this calculation. So number 2, the second number 2, the one we actually did a calculation with, we did a large tank where we said R1 is a lot greater than R2. Okay? And if R1 is a lot bigger than R2, then we can say that V1 is essentially 0. Okay? And that's what that's referencing, that last line, that we can assume that this water level is constant and that the velocity is 0 and it's not dropping. So we can say that basically, is this tank going to eventually empty out? And the answer is yes, with time it will eventually drain. But if I watch this, because this is so much bigger than this is going to drop really slow. And the number we calculated was like 0.22 millimeters every second on that other calculation. So it's not really 0, but it's an estimation, it's an approximation that'll get us pretty good data. It's not going to be perfect. But this is going to be a 2-location problem. So we're going to talk about location 1 and we're going to talk about location 2. So this would be my V1 and my R1, and then this would be my R2. And the question being asked is, how fast is that water going to come out of the hole? Now, there's a few things we need. We want velocities, we want heights, we want P's, and we want radiuses and areas. Okay, so we want a P1, we're going to want a P2, we're going to want an H1, and we're going to want an H2.